Welcome to the second module of nonlinear vibration. So, in the first module we present you about the introduction of nonlinear systems, and in this module we are going to discuss on the derivation of nonlinear equation of motion. So, in the first three classes I will tell you about this force and moment based approach, generalized D'Alembert principle, Lagrange principle, extended Hamilton principle for single multi-degree of freedom and continuous system. In the fourth class, we will see the development of temporal equation of motion using Galerkin method for continuous system, and again on the fifth class we are going to rediscuss about this ordering technique, scaling parameters, bookkeeping parameter, and commonly used nonlinear equations like Duffing equation, Van der Pol equation, and Matthew and Hill's type of equation. So, already we have discussed or we have seen these four different types of equation and a combination of this Duffing and Van der Pol equation or Duffing and Matthew equation and Matthew Hill equations. So, in combination of all these equations, so we can have other forms of nonlinear governing equations. So, today class we will study about the force and moment based approach. So, before that we will initially review what we have discussed in the last 4 lectures. So, in the last 4 lectures we have discussed about this linear and nonlinear systems. So, this linear and nonlinear systems can be grouped based on the superposition theory. So, if the system in the system we can apply superposition theory, then it can be a linear system, otherwise the system can be a nonlinear system, and in case of superposition theory it has to obey the additive rule and the homogeneous rule. So, both homogeneous and additive rule can be checked to see whether the system is a linear system or the system is a nonlinear system. And in case of a nonlinear system, we can order the magnitude or order the nonlinear terms by using the scaling parameter or bookkeeping parameter, and also we have discussed about different type of response observed in case of this nonlinear system. So, generally the vibrating response can be the transient response or the steady state response. So, in case of steady state response, we have discussed 4 different types of response, that is fixed point response and periodic response, quasi periodic response, and finally the chaotic response. So, we have discussed about the equilibrium points in case of the steady state response. As in case of steady state response, the response is independent of time, then we can find the equilibrium position by putting this time dependent term equal to 0 and finding the response of the system. So, the response may be fixed point, periodic, quasi periodic and chaotic. In case of periodic response also, the response may be harmonic or other different types of periodic response, but other periodic response can be reduced to that of the harmonic response. And in case of quasi periodic response, so it may be aperiodic response in which the different frequency bear irrational ratios. For example, I can write this response y equal to 5 cos 2t plus cos 2 root 5 t. So, the resulting response will be a quasi periodic response with frequency 2 and 2 root 5, and the ratio between these two, that is 2 root 5 and 2, that is root 5, is an irrational number. So, the resulting response is quasi periodic. Similarly, we have seen when the response is neither fixed point, periodic or quasi periodic, then the response is chaotic response. Also we have seen the period doubling route to chaotic response. And after studying this equilibrium point, so we have briefly discussed about the stability and bifurcation of the responses. So one can observe different type of response or response type or bifurcation types also. So this example represent a saddle point, the equilibrium point is a saddle point. Here the equilibrium point is x equal to 0. So this point is x equal to 0, this is the equilibrium point, and the flow around this equilibrium point is shown here. So this is a saddle point. So clearly the solution x double dot minus x equal to 0. So one can find the solution. So one can write the auxiliary equation in this case. For example, this is x double dot minus x equal to 0. So the auxiliary equation can be written as d square minus 1 equal to 0 or d equal to plus minus root over 1. So this is equal to plus minus 1. So as the roots are plus minus 1, so the solution becomes, so x will be equal to a1 e to the power I e to the power t plus a2 e to the power minus t. So due to the presence of e to the power t, which is exponentially growing, and e to the power minus t, which is decaying exponentially, so one can have a response like this around the equilibrium point, that is x equal to 0, and one can have, these are the asymptotes. So these are the separatrix dividing these points. Similarly, one can have a response x double dot plus x equal to 0, which will give a center. So for example, so for this case x double dot plus x equal to 0. So in this case the auxiliary equation equal to d square plus 1 equal to 0 or d equal to plus minus root over minus 1, that is plus minus I. So its solution will be, so x equal to a1 e to the power I t plus a2 e to the power minus I t. So where t is the time. So one can write this term. So as it is known that this e to the power I theta equal to cos theta plus I sin theta. So by substituting this thing, one can write this equation in this form: x will be equal to c sin t plus phi. So where this phi and c can be obtained from the initial condition. So one can have the center in this case. So this will give a periodic response, so whose phase portrait can be look like this. Similarly, one can have a stable spiral in this case and stable node in this case of a. So this is the second order equation with a damping term. So here the damping term is, damping factor is 3. So one can find the solution and one can see this is a stable node. So we have divided the dynamical system into discrete time system and continuous time system. So in case of the discrete time system, we are dividing the system, or we are finding the system response at k plus 1th time as a function of kth time, and in case of this continuous system, so we are dividing this thing to autonomous and non-autonomous system. So in case of non-autonomous system, so x dot depends explicitly on the time parameter, and in case of autonomous system, it does not depend explicitly on time. So for these cases already we have discussed about the fixed point by substituting this x dot equal to 0. So we can write the fixed point equal to f x m equal to 0. So here m is the control parameter. So either by linearization near the equilibrium position or by perturbing, so we can find or we can study the stability of the system. So by taking a small parameter near the equilibrium position x 0. So, one can write the governing equation y dot equal to f x 0 plus y controlling parameter m 0, and by expanding this thing using Taylor series, one can write this y dot equal to f x 0 plus y m 0 plus d x f x 0 m 0 y plus higher order terms. So, neglecting these higher order terms, so one can write y dot equal to d x f x 0 m y, or this term one can write as A. So, A is the Jacobian matrix of the system. So, A is the Jacobian matrix which is function of first derivative of the system with respect to different parameters. So, by finding the eigenvalues of this Jacobian matrix, so one can study the stability of the system. So, this will give the local stability of the system. So, if one plot the eigenvalues in the real and imaginary plane, so if all the roots are on the negative side of the S plane, then the system is stable, otherwise the system becomes unstable. So, one can classify this stability of equilibrium point by hyperbolic fixed point. When all of the eigenvalues of A have non-zero real parts, then it is hyperbolic fixed point, and if all the eigenvalues of A have negative real part, then it is known as sink, and if one or more eigenvalues of A have positive real parts, then it is source. That means, if all the real parts are negative, that is they are on the left side of the S plane, then the system is stable, and if some of the roots are on the right hand side of the S plane, then the system is unstable. So, due to this nature, the response of the system grow, and that is why it is known as sink, so source. But when it is in the left hand side of the S plane, then as the system is stable, that is why it is known as sink. So, the sink can be a stable focus or a stable node also. Similarly, the source can be a unstable focus or unstable node, and when some of the eigenvalues have positive real parts while rest of the eigenvalues are negative, then the point is known as a saddle point. Similarly, if some of the eigenvalues have negative real parts while the rest of the eigenvalues have zero real parts, then the system is marginally stable. So, in case of marginally stable, some of the eigenvalues have zero real part and most of the eigenvalues have negative real part. So, in this case the system is marginally stable, and we have also briefly reviewed about the bifurcation of the system. So, this is a French word introduced by Poincare. So, we can have local bifurcation, global bifurcation, and bifurcation points also, and a co-dimension M bifurcation. So, a bifurcation that required at least M control parameter to occur is known as co-dimension M bifurcation, and the location of the bifurcation point is the bifurcation, the location at which the bifurcation occurs, that is the bifurcation point. Similarly, we can classify the bifurcation into continuous and discontinuous. So, in case of continuous, it is static bifurcation and dynamic bifurcation, and in discontinuous it is dangerous or explosive. In case of static bifurcation, one can have these three different types of bifurcation, that is saddle node, pitchfork or symmetry breaking, and transcritical bifurcation, and in case of dynamic bifurcation, so it is Hopf bifurcation. So, in case of pitchfork or symmetry breaking, so the response may be supercritical, or so this is supercritical, or it may be subcritical also. Similarly, in case of Hopf bifurcation, one can have supercritical and subcritical bifurcation. So, these examples already we have seen. So, for example, in this case x dot equal to mu minus x square. So, the equilibrium point becomes mu minus x square equal to 0. So, one can find the equilibrium position mu minus x square equal to 0, and by plotting that thing one can have these two lines. So, for example, for its eigenvalue, we can find the Jacobian matrix by differentiating this thing. So, by differentiating this, one can get the A equal to minus 2x. So, A equal to minus 2x. So, A minus lambda I becomes minus 2x minus lambda. So, lambda becomes minus 2x. So, as lambda becomes minus 2x. So, when x equal to plus root mu, so then the system has lambda negative. That is why this branch is stable and this branch is unstable. So, this point is saddle node bifurcation point, and similarly here for a two dimensional equation, that is in terms of when the equations are written in terms of A dot and gamma dot, where A is the amplitude and gamma is the phase response of the system. So, this is for a typically used nonlinear system. So, in this case one can have the saddle node bifurcation point at these 2 points. So, if one plot the eigenvalues, so one can study that this portion the response is stable, and after that the system is unstable. So, at this point the system may experience a jump up phenomena. Similarly, at this point also the system may experience a jump down phenomena. So, while reducing this control parameter, so from this position the system response may jump down to this stable solution. Similarly, here when we are sweeping up the frequency, so at this point the system will have a tendency to jump up as this branch is unstable. So, similarly we can study the Pitchfork bifurcation. So, in case of Pitchfork bifurcation, so these two are Pitchfork bifurcation. So, this is supercritical Pitchfork and this point is supercritical, as from when we are decreasing the response. So, from a positive from a stable response it goes to a stable non-trivial branch. So, this is the trivial branch, this is the non-trivial branch. So, the trivial branch become unstable, but the non-trivial branch becomes stable. So, this point is a supercritical Pitchfork bifurcation point, but this point, so initially we have one stable trivial state, but after this bifurcation point we have both unstable trivial and non-trivial response. So, as both the trivial and non-trivial response are unstable, so from a stable branch we are getting unstable branch, that is why this is subcritical Pitchfork bifurcation point. So, the subcritical bifurcation point is a danger or catastrophic failure point. So, at this point if one increase this control parameter omega bar, so then the system will have a tendency to jump up. So, here it will jump up to the upper stable branch. So, in case of this nonlinear system, one can observe that at a particular control parameter one have multiple type of response or multiple solutions present in the system. So, in this case before this bifurcation point the system has a bistable region and one unstable region. After this bifurcation point the system has only one stable region, and between these two supercritical and subcritical bifurcation point the system have one stable and one unstable response, fixed point response. So, these responses are fixed point response. In case of transcritical bifurcation, so for example, one can take some. So, in this case, in case of transcritical bifurcation, so this point, so this is the trivial branch, this is the non-trivial branch. The trivial and non-trivial branch they change their stability. So, the trivial branch become unstable and the non-trivial branch which was unstable before becomes stable. So, this is a transcritical bifurcation point. Similarly, one can have this Hopf bifurcation in which the fixed point response becomes periodic response after the bifurcation. So, if it becomes a stable periodic response, so from a stable trivial response it becomes a stable periodic response, then this is known as supercritical Hopf bifurcation. But if from a unstable trivial branch it becomes again unstable, or from a stable trivial branch the periodic response become unstable, or from a periodic stable periodic response the resulting response become unstable. So, the resulting response becomes unstable, then this becomes subcritical Hopf bifurcation point. So, from a stable fixed point if you are getting stable periodic, then it is supercritical, and from a stable fixed point if you are getting unstable fixed point and unstable periodic response, the resulting response is, or resulting bifurcation is subcritical Hopf bifurcation point. So, in this way we know the different bifurcation point, that is static and dynamic bifurcation points for the fixed point response. So, these things will be used in our later analysis. So, already we have discussed about different type of multi-stability region, and in this multi-stable region, so one should know to which response one has to. So, at a particular control parameter, so one can have multiple. So, this is a fixed point, this is another fixed point. So, it has two. So, these two fixed points are stable, but it has one unstable. So, to know to which stable branch the system response will move from a initial point. So, one can plot the basin of attraction. So, here the basin of attraction has been plotted by taking different initial conditions. So, these initial conditions one can take by considering, one can make different grids, and by taking different initial conditions, so one can plot the responses. So, here one can clearly observe two. So, one can clearly observe two stable response. So, these correspond to, so this is, so one can clearly observe two stable response and a saddle node here. So, saddle node correspond to the unstable response of the system. So, this is unstable response of the system, and one can have a stable response also. So, near 0, so this point correspond to these and these correspond to the stable branch, and this point correspond to the unstable branch. Also, in previous classes we have reviewed about different type of periodic response, phase portrait, and how to analyze these responses using Poincare section. So, in case of a periodic response, we have seen that the Poincare response can be shown as a single point, and in case of a quasi periodic response, the Poincare section can be a closed curve, and in case of a chaotic response, the Poincare section will fill up the phase portrait. So, we have discussed about different elementary parts of a vibrating system. Today class we are going to derive the equation motion by using this Newton's method or D'Alembert principle, so which are based on the force and moment equations. So, already we know different elementary parts of the vibrating system. So, one required a means of storing potential energy. So, that means when it is at its extreme position, it has only potential energy. When it is coming down, then this potential energy is converted to kinetic energy, and so on. At this point, at the equilibrium point, due to inertia, the system moves up and the motion continues. So, one required a disturbing force, restoring force, inertia force and damping force for finding the equation motion for the system. So, one can have different type of or different methods to find the equation of motion of a system. So, these are inertia based approach. So, one is Newton's method, Newton's second law, one can apply Newton's second law or D'Alembert principle to find this equation motion. Also energy based approach, so in which one can apply this Lagrange principle and extended Hamilton principle to find the equation motion. So, given one physical system, so these are the steps one can follow to find the equation motion or to study the system. So, first one has to convert the physical system to simplified mathematical model, then determine the equation motion of the systems, then solve these equation motion to obtain the response and finally, interpretation of the result for the physical meaning of the system is required. So, during this course of nonlinear vibration, so we will carry out all these 4 steps to study different systems. So, for example, let us see one system. So, we can convert a physical system by using this equivalent inertia, equivalent stiffness and equivalent damping, and for finding the equation motion we may use this inertia based method, that is Newton's second law, D'Alembert principle or energy based principle like Lagrange principle and extended Hamilton's principle. So, if we have a moving coordinate frame, so this Newton's second law or D'Alembert principle and this, so we can apply for rigid bodies with fixed coordinate frame. So, if we have moving coordinate frames, then we can go for this Newton-Euler formulation, Lagrange-Euler formulation or generalized D'Alembert principle in this moving coordinate frame. So, moving coordinate frame problems will come, for example, in case of a robotic manipulator. So, in case of a robotic manipulator, let us take 2-link robotic manipulator. So, in this case, the end effector position and orientation can be represented from with respect to this base by using different moving coordinate frame. So, one can attach coordinate frame to this base and at this link point also and at the end effector point also. So, one can write the equation motion in terms of all these coordinate frames. So, in that case, so one can use this Newton-Euler formulation, Lagrange-Euler formulation or generalized D'Alembert principle based on this moving coordinate frame. So, let us see. So, this is the different methods for converting a physical human body to different dynamic systems. So, mathematical modeling can be obtained by initially using the simplified models of a human body. So, one can attach different or one can write the whole human body as different spring and mass system. So, these are a different spring and mass system from the leg position to the head position of the body, or one can develop another type of model where this portion can be represented as the spinal cord of the system, then these are different spring and mass damper system. So, this is the head, starting from the leg and head we can attach different spring and mass and we can convert the human body to a different model, different dynamic model, and this dynamic model can be simplified by putting this simplified model. Also one can combine these two and we can write a single mass and the spring damper, and this part is here, and one can have this 3 mass and 3 spring system. So, this is in standing position, and in sitting position also one can develop different models. So, these are 4 different models developed in case of the sitting position, and these are the 4 different models developed in case of the standing position, and this work has been taken from this Garg and Ross human body vibration IEEE transaction on system, man and cybernetics 1976. So, this is in the sitting position. So, the person is sitting on a chair. So, if one can model this thing, one can model this whole system by this spring and damper system. So, the leg part is modeled as two rigid body with the joint shear. So, by taking all these spring and damper, so spring mass damper, one can develop a lumped parameter model for this system. Similarly, one can develop different type of lumped parameter model for different types of system. For example, so in case of a lathe machine, so the lathe machine can be modeled as a, so this side one can model this as a spring and mass damper model, spring and mass model. So, this is the mass of the headstock M1 and this is the mass of the tailstock side. So, this is tailstock side and this is headstock side and this is, so this is the lathe bed. So, we are considering the mass to be of the bed to be 0, or one can model this as a mass, eccentrically placed mass also. So, the mass can be put at this position. So, in all these cases one can have different coordinate systems. So, in these coordinate system one can put different physical coordinate system with respect to a particular coordinate frame and develop the equation motion. So, depending on the coordinate system used, so one will obtain a coupled equation or uncoupled equation of motion. So, for example, in this case, so one can have two different type of coordinate system. One can use this physical coordinate system or one can use generalized coordinate system. So, as this is a 2 degrees of freedom system. So, one can have the displacement x1 here, displacement x2 here, or one can represent this thing by displacement of this side and the rotation of this side also. So, one can represent this equation in terms of x1 and theta. So, either one can represent by only translational displacement at these two ends or by using this one translational and one rotation. Also, these points can be changed and one can get different type of equation. So, depending upon the chosen coordinate system, one can obtain a coupled or uncoupled equation motion. So, this equation motion can be, or a generalized equation motion for a multi-degree of freedom system can be written in this form. So, let for a 2 degree of freedom system, so it will be M11, M12, M21, M22. So, into x1 double dot, x2 double dot plus k11, k12, k21, k22, x1, x2. So, this is equal to, so in case of a free vibration, so this will be equal to 0, 0. So, in this case, if the off diagonal terms are present, then the system is coupled. So, this is dynamically coupled. If the mass matrix is coupled, then the system is known to be dynamically coupled, and if the stiffness matrix is coupled, that is the off diagonal terms are present, then the systems is known as statically coupled. So, if it is uncoupled, then we can get the advantage of this like this. So, let the off diagonal terms are 0. So, in that case I can write this system equation in this form. So, it can be written in this form y1 double dot, y2 double dot plus k11 0, 0, k22. So, this is y1 and y2. So, this will be equal to 0, 0. So, for the coordinate y1, y2, the equation is uncoupled. So, in this case the equation can be written as m11 y1 double dot plus k11 y1 equal to 0, and the second equation will be m22 y2 double dot plus k22 y2 equal to 0. So, it can be reduced to two first order, it can be reduced to two single degree of freedom equations. In this case, the equations are coupled, but in this case the equations are uncoupled. As it is uncoupled, so one can solve this equation as m y double dot plus k y equal to 0, that is that of the single degree of freedom system. So, one can get the solution easily by decoupling these equations. So, there are several methods to decouple the equations. So, one can use this modal analysis method to decouple these equations. So, today in class we are going to study about the Newton's second law and D'Alembert principle, and we will apply this thing to different systems. So, according to Newton's second law, a particle acted upon by a force moves so that the force vector is equal to the time rate of change of linear momentum vector. So, let this mass m is acted upon by a external force A, and an acceleration of A is produced in the system. So, in this case, according to this second law, so F will be equal to time rate. So, this vector is equal to the time rate of change of linear momentum. So, linear momentum equal to m. So, if it displaced by a vector r, if the position vector r represent the displacement of this body of mass m, then the change in momentum. So, this is equal to m dr by dt. So, one can write this equation as F equal to m a, where a is the acceleration, F is the external force. So, external force equal to mass into acceleration. This is second law, Newton's second law. But if in a moving system, let the system is moving with an acceleration a. So, if a force of minus m a is applied to the system, then the body can be in equilibrium. So, F minus m a will be equal to 0. So, from this equation 1, one can write F minus m a equal to 0. That means, summation of the external force and the inertia force. So, summation of external force F plus this inertia force equal to 0. So, this is D'Alembert principle. So, one can obtain the D'Alembert principle from this Newton's second law by adding this inertia force to the moving system. So, in this way one can convert a dynamic system to one static system by adding the inertia force. So, the inertia force is a force which acts in a direction opposite to that of the acceleration, and by adding the external force with the inertia force, we can convert this dynamic system to an static system. So, the disadvantage of this system is that the parameters we are using, that is this force and this acceleration, are all vector terms. So, it depends on both magnitude and direction. So, depending on the direction, if there is some ambiguity while calculating or while analyzing the system in the consideration of the direction, then the obtained equation motion will be erroneous. So, it is advisable to use scalar terms to develop this equation motion. So, by using the scalar term, that is, for example, the potential energy and kinetic energy terms, to write the equation motion. So, one can use this virtual work principle, but virtual work principle is applicable only for the static system. So, by applying this D'Alembert principle, as we are converting this dynamic system to an equivalent static system, Now, one can apply this virtual work principle to this equivalent static system. So, by using this D'Alembert principle, so after converting this dynamic system to a static system, now we are in a position to apply this virtual work principle. So, that is generalized D'Alembert principle, which we will study in detail. So, while applying this Newton's second law, so one should know about the inertial frame. So, this inertial frame are the reference frame at rest or moving uniformly relative to one average position of a fixed star. Quantities measured relative to this inertial frame are said to be absolute. So, let us take or let us use this Newton's second law to derive the equation motion of this simple pendulum. So, a simple pendulum, in case of a simple pendulum, this is a bob with a massless rod. So, let me write, this is my coordinate frame x y. I can use a coordinate frame x y, or I can use another coordinate frame also. So, I can take a unit vector along this direction, that is, and along this direction. So, I can take, so this is the, let me take, this is unit vector along this, and perpendicular to this is the j, and this represent the tension in the string. So, while moving, so this is the free body diagram of this, bob. So, in which the physical coordinate system can be shown either in terms of x y or using another coordinate system, that is in terms of unit vector I and j. So, the total force acting on the system can be written. So, this is the force, tension force T, and another force will act on the system. So, this is mg. So, under the action of these two forces, the system will be in equilibrium if we add the inertia force to the system. So, the acceleration at this point is of two type. So, if it is rotating by an amount theta, so it has a tangential acceleration. If it is rotating in this direction, you have the tangential acceleration term this, that is equal to L theta dot square, and another term also we can have. So, this term equal to L theta double dot, and another term which is towards the center of rotation, that is equal to L theta dot square. So, for a moving string, for a moving or rotating, so this rotating bob, so we have two. So, for this rotating bob we have two terms in acceleration. One is the tangential term, that is L theta double dot, that is L alpha, theta double dot is the angular acceleration, and theta dot is the angular velocity. So, we have the centripetal acceleration, that is L theta dot square, or this is the acceleration towards the center, that is the centripetal acceleration, that is L theta dot square, and another term, that is the tangential term, this is L theta double dot. So, this is subjected to a force T, that is tension, and mass m, and this mg force, mass into acceleration due to gravity, mg force can be divided into two parts. So, one is tangential to the path, and other one acts along this direction. So, this is equal to mg cos theta, and this term equal to mg sin theta. So, as T will be equal to mg cos theta, then the resulting force acting on the system equal to mg sin theta, and the inertia force also acting on the system. So, total force acting on the system, external force on the system equal to, so as I am taking a coordinate system I in this direction. So, it will be minus t and mg cos theta, minus t plus mg cos theta I minus mg sin theta j. So, this direction, as this direction is taken positive j. So, this is negative j. So, this is minus mg sin theta j. So, this equation becomes minus t plus mg cos theta I minus mg sin theta j. So, this is the force, external force acting on the system. So, according to Newton's second law, this external force equal to mass into acceleration, and already we have written this acceleration in terms of ij like this. So, A will be equal to, as we have taken this as the positive I. So, it will be minus L theta dot square I, and this is positive direction of j. So, this becomes L theta double dot j. So, L is the length of the simple pendulum. So, now by substituting this f equal to ma, so we can write the equation like this. So, f equal to ma. So, f equal to minus t plus mg cos theta I minus mg sin theta j. So, this will be equal to m into minus L theta dot square I plus L theta double dot j. So, by equating the ith component and jth component, so I can write the equation motion of the system. So, it will be m L theta double dot plus mg sin theta equal to 0, or by dividing this by m L, this equation reduces to theta double dot plus g by L sin theta equal to 0. So, when theta is very small, one can write this equation in this form, theta double dot plus g by L theta equal to 0. So, this will lead to simple harmonic motion. So, where omega n equal to root over g by L. But if theta is not small, so one can expand this theta in this form, theta minus theta q by factorial 3, or sin theta equal to theta minus theta q by 6. So, this resulting equation becomes theta double dot plus g by L theta minus theta q by 6 equal to 0. So, one can write the expression for tension in this form also. So, T equal to mg cos theta plus ml theta dot square, or one can write, so this is equal to ml theta dot square plus g cos theta by taking m common. So, this way one can find the governing equation of the system by applying Newton's second law. So, while applying Newton's second law, one can write the equation motion in this vector form. First one can write the acceleration, and then one can write the force term, and by equating the force equal to mass into acceleration, one can find the equation motion. So, this simple example illustrate how one can use this Newton's second law to derive the equation motion. So, one can have, so in this case we have taken, or we have derived this equation motion by considering force equal to mass into acceleration. But if you can consider this as a rotating system, so in that case also we can write the Newton's second law, or Newton's second law can be written in this form: the moment of a force about a fixed point is equal to the time rate of change of the angular momentum about that point. So, after finding the external force, so this external force acting on this, so this is T and this is mg sin theta, and this term equal to mg cos theta. So, we can write this m 0. So, this equation can be written m 0, that is moment about this point O due to this external force will be equal to rate of change of angular momentum. So, this is rate of change of angular momentum. So, we can find, so this m 0 equal to r cross f. So, already we know f, and r equal to, in vector form if you write, so r will be equal to L I. So, r equal to L I, and we can write this m 0 equal to r cross f. So, this becomes L I cross mg cos theta minus T I, and then minus mg sin theta j. So, as we are having this cross product, then so I cross I, this becomes 0. So, we will have I j, that will be represented by k, I cross j equal to k. So, this becomes minus mg L sin theta k. So, m 0 becomes minus mg L sin theta k. So, h 0 now you can find. So, h 0 dot will be equal to r cross acceleration term. So, acceleration equal to m r double dot. So, L I cross, so r equal to L I. So, cross m L theta double dot j minus m L theta dot square I. So, this becomes m L square theta double dot k. Now, by equating these two terms, one can find the equation motion to be this. So, what we obtained before, the equation motion equal to theta double dot g by L sin theta equal to 0. So, one can write the nonlinear equation motion by expanding the term sin theta equal to. So, sin theta equal to theta minus theta q by 6. So, in this way one can write the equation motion. So, as we have discussed previously, so one can obtain the potential well, and one can study the response of this system qualitatively. So, one can write a program, simple MATLAB program, to find the potential function. So, potential function f theta will be equal to, so in this case f theta equal to g by L sin theta. So, capital F theta will be, so this will be equal to g by L sin theta d theta. So, this is 0 to L. So, one can find this f theta. So, this will be g by L minus g by L cos theta. So, one can, so in this case it is written. So, f equal to omega square cos theta. So, one can similarly find the theta dot term, and if one plot, so this is the potential function and the resulting phase plot for the simple pendulum. So, these are the center point and these are the saddle node points. So, it has been plotted for different angular position of the pendulum. So, these are the center point and these are the saddle node point, and these are the separatrix which separate, and in between the separatrix we have this homoclinic and heteroclinic orbits. So, these are the homoclinic orbits and these are the heteroclinic orbits, and one can study the flow around these saddle node and center points also. So, one can study also the work energy principle, which is required to derive the generalized D'Alembert principle. So, which we required for finding, or we required for converting this vector form of equation motion to a scalar form, or to derive the equation motion using the scalar form like potential energy, kinetic energy. So, we can convert, or we can use this work energy principle, and according to work energy principle, the work performed in moving a particle from position 1 to 2 is equal to the change in kinetic energy. So, work done equal to F dot dr. So, from position r1 to r2, so one can find this is the potential work done. So, this work done equal to the change in kinetic energy. So, work F, one can write this F equal to m r double dot. So, one can write this thing equal to d of half m r dot, and this thing can be written in this form. So, this is equal to T2 minus T1. So, the work done in moving a body from or particle from position 1 to 2 equal to change in kinetic energy of the system. So, force for which the work performed in moving a particle over a closed path is 0. So, considering all possible paths are said to be conservative forces. the work performed in moving a particle over a closed path beginning at a given point and returning back to the same point. So, if it has started from this and it has come back to the same point, then the work done is 0. Similarly, in a system, if the work performed in moving a particle over a closed path is 0, considering all possible paths, then the applied force is said to be a conservative force. The potential energy can be defined as the work performed by a conservative force in moving a particle from an arbitrary position to a reference position. So, the potential energy is defined by the work performed by a conservative force in moving a particle from a arbitrary position. So, arbitrary position R to the reference position this. So, the work done one can find, and that will be the potential energy of the system. So, work performed by a conservative force in moving a particle from R1 to R2 is equal to the negative of the change in potential energy from V2 to V1. Work performed by non-conservative forces in carrying a particle from position R1 to position R2 is equal to the change in its total energy. Work performed by non-conservative forces in carrying a particle from position R1 to R2 is equal to the change in total energy of the system. So, already we know about D'Alembert principle. So, it states the vectorial sum of the external forces and inertia forces acting on a moving system is 0, and now one can use this to state the generalized principle of D'Alembert, like the virtual work performed by effective forces through infinitesimal virtual displacement compatible with the system constraint is 0. So, one can write the work done equal to, so this is the inertia force. So, Fi minus, so this is the equivalent force of the system dot delta Ri equal to 0. So, the virtual work equal to 0. So, this is D'Alembert principle. Now, by using this D'Alembert principle, one can derive the Lagrange principle and the extended Hamilton principle of the system. So, in extended Hamilton principle or Lagrange principle, the terms used are potential energy and kinetic energy. So, these are scalar terms. So, that does not depend on those two terms does not depend on the direction of the system. So, one can easily find the equation motion by using those scalar terms. Now, one more example we can see. So, in this case we have to derive the equation motion for this cantilever beam, large cantilever beam, which is subjected to a periodic force y equal to y0 sin or cos omega t. So, let it is y0 cos omega t. So, in this case one can take these assumptions, you can assume this as a Euler-Bernoulli beam and derive the equation motion. So, by using Newton's second law, one can write the bending moment equal to EI. So, this is the nonlinear. So, assuming large deflection or moderately large deflection. So, one can write the bending moment, and now by using this inertia term, so one can write this bending moment minus this inertia bending moment due to this inertia equal to 0, and one can derive the resulting equation motion. So, one can model the system like a spring mass damper system with moving base and find the equation motion also. So, let us see some quiz problem. So, derive the equation motion of a rotating beam with end mass model as a lump parameter system. Then derive the equation motion of a base excited cantilever beam with arbitrary located point mass using D'Alembert principle. Discuss about the bifurcation of fixed point responses, how the response of a linear and nonlinear systems are different. So, for the first one you may refer. So, this is the system. So, you can model the bending of the system like a bending spring, and this mass, you can take this mass of this part empty plus mass, elastic mass. So, it can be taken as the elastic mass, the lumped mass is present here, that is MT plus ME, and this is the bending spring. So, this ME can be obtained from this equation. Similarly, the K can be obtained, the stiffness can be obtained from this equation, and the governing equation can be written in this form. So, these are brief hints given for deriving the equation. Similarly, for a base excited system, so you can refer the paper by Kaur and Dwivedi 1999. So, this paper is from International Journal of Nonlinear Mechanics. So, the equation motion can be derived using this D'Alembert principle by taking a small element, by writing the bending moment at this point, one can derive the equation motion. So, in this way you can derive the equation motion. So, next class we will use the Lagrange principle and extended Hamilton principle to derive the equation motion of different systems. Thank you.